necessarily talk about but I want to get rid of scholarship. So basically, just quickly my first year, got like 7 to the area, but they're pretty knocks to kids. I donate other things. It's fun. I've lost it.
Okay, so I think it is time to start now, right? So I think it's time to start now, right?
Yes. Okay, so you've done this one at least once, but I just need to see it again. It's number 15 on the practice exam. And it has to do with the truck traveling down a hill when the brakes lock. That's an angle. And there's kinetic friction is given. We have to figure out how far the truck's going to slide before. And you said that you wanted to put this one on the exam, so.
Yeah. My biggest worry is that we're not going to do very well on this one, but if I divide it into multiple questions, maybe people are going to do well. I don't know. So we're talking about problem number 15. And that problem is direct application of the work energy theorem, even though you can solve it without thinking about energy at all. But the standard and shorter way is using the work energy theorem. So this is what you have. Here is the slope. Here is the initial position of the truck. Here is the final position when it is at rest. And choose the zero height to be at this final position. And let's see what is given. You have the initial velocity is v naught equal to 11.1 meters per second. The final velocity, of course, is 0. The angle is given 17 degrees, or let's call it theta. And what else? Kinetic friction 0.74. Kinetic 0.74. They're asking us to find the stopping distance. So the distance from here to here, this distance. So if you use a coordinate system, that is x direction here, y direction here, positive x direction. You're looking for this length, which is exactly the displacement x. They're asking what is the displacement. X is what? And well, so maybe start with finding the height. The height h. So it is not known, you cannot calculate it, but you can express that height h in terms of the unknown distance x, unknown stopping distance x, by using this right triangle. So you can say that the height h is equal to the unknown distance x that you're looking for, multiplied by sine of your angle. And now you have initial energy of this truck is going to be kinetic part 1/2 m v initial squared. The mass is unknown. Hopefully the mass is going to cancel out.
That's E what? What was the subscription?
Initial, or okay, initial. For initial. plus gravitational potential energy mgh, where h is this. So I can write it as 1/2 mg naught squared plus mg x psi. The final energy of the Turk is 0 because I chose the 0 height to be here. And the Turk is at rest, so it doesn't have, it has 0 kinetic energy. Now, while the truck is moving in this direction, it is going, the friction force is going to do work. And the friction force is the only non-zero force. And the work energy theorem says that the work done by the friction force has to be equal to the change of energy of the truck. In other words, the work done by the friction has to be equal to final minus initial energy. In other words, the work done by the truck has to be equal to negative initial energy because the final energy is 0. So now let's figure out what is the work done by the friction force. So I need the diagram. So this is the slope, this is the truck, the horizontal, and I need the free body diagram. So in the free body diagram, you have the weight mg of the truck, you have the normal force F normal, and you have the only other force is the friction force right here. Now, you have to decompose, using this coordinate system, you have to decompose the force that is not along the coordinate axis. And that force is the weight. So you decompose it into x and y components, something like this. So this is going, so here is the y component of the weight, here is the x component of the weight. So those are components. So you have to, we're going to use those components instead of the weight because those components are in directions that are along the coordinate axis. So here is the y component, here is the x component. And of course, the angle between them is 90 degrees. The angle theta is going to appear here because of angles with mutually perpendicular arms. The component of the y component of the weight, this is going to be equal to mg times cosine of the angle theta. And since the truck is not flying above the road or sinking below the pavement, that component of the weight should be exactly equal in magnitude to the normal force. So again, this became, yes.
How come that y of the weight is mg cosine? Should it be mg sine?
No, because the definition for cosine of an angle is
sorry.
adjacent divided. So sometimes the y component is calculated with cosine rather than with sine.
Depending on where the
Depending upon, you have to look at the triangle. This is why we do the construction. And if we have problem of this type in the test, the correct diagram is going to be worth probably close to half of the points for the problem. So keep that in mind. So this is why I drew the diagram on a separate place, the free body diagram in a separate place, so it to be visible and it to be clear. Okay, so this means that the friction force by definition is a product of the coefficient of friction times the normal force. And again, the diagram tells me the normal force is exactly equal to the y component of the weight. In other words, the friction force is coefficient of friction multiplied by mg cosine of the angle. So I have, this is the magnitude of the friction force. The work done by the friction force is, by definition, it is the magnitude of the friction force times the magnitude of displacement. The displacement is what we're looking for, times cosine of the angle between the displacement vector and the friction force vector. So displacement is down this way, friction force is exactly in opposite direction. The angle between them is 180 degrees. So you have cosine of 180, which is exactly -1. So this means that the work done by the friction force is going to be negative. Instead of friction force, I'll write it's equal. So it is, I'll write first maybe coefficient of friction, mg. I'll write the factor of x here. And after that, I have to say cosine of the slope. The minus sign came from the. And now here is the work energy theorem. That work has to be equal to this. So since the work is equal to negative initial energy, I have the work is negative coefficient of friction mg x cosine of theta. This should be equal to the initial energy with negative algebraic sign, which is going to be negative algebraic sign 1/2 mv initial squared plus mg x sine of that. And that's it. So here, the only unknown is going to be the displacement x after you cancel out the mass. You can multiply by -1 to get rid of the negative signs. So the terms that contain the unknown are this and this term. So put those two terms on the same side of the equation. So multiply by -1. So this term is unchanged, coefficient of friction times g times x times cosine of theta. The other one comes here with negative algebraic sign, g times x times sine theta. And what is left on the other side of the equation is 1/2 v naught squared. And that's it. Now factor out, let's say, factor out g times x. In the brackets, you're going to have coefficient of friction times cosine of theta minus sine of theta. And on the other side, you have v naught squared divided by 2. And that's it. Now solving for x, you get that the displacement x is going to be v naught squared divided by 2 times g times the expression of the brackets times cosine of theta minus sine of theta. And now you can substitute the numbers and see if the answer, the numerical answer is correct. Yes.
So my one question is, if you go to the very top of the board, you've got the frictional force of K just underneath that, work equals the frictional force, the kinetic frictional force times the cosine of 180.
Times the displacement times the cosine. This is x is the displacement. So by definition, the work done by a force is equal to the magnitude of the force times the magnitude of displacement times the cosine of the angle between them. The displacement is this, from here to here. This is the displacement x. The force of friction is this way. So the angle between them is 180.
When would it be different then?
The work done by the friction force, kinetic friction force, is always going to be, the angle is always going to be 180. Kinetic friction force, angle always 180, and cosine of 180 is -1, always. So I don't want you to look at this problem as something very complicated that I want to give in order to make your life harder. But on the other hand, a problem of this type is examining multiple issues. The concept of energy, the concept of work, and the composition of forces. So I am tempted, and this problem can be, I can change it in different ways. So I can make the truck to go uphill, I can give you the stopping distance and ask you to calculate the coefficient of friction, or all kinds of different variations. I can give you the stopping distance and ask you to find how fast the truck was traveling. So many variations for the multiple versions of the test, if we go that way. But again, I don't know. What do you think about this problem?
There's a lot to it. I think this makes sense. I think if you were to throw like a different variable, like the speed, I think that'd be kind of tricky, but I feel like it'd be pretty straightforward if you can.
In accident investigations, you know the stopping distance because you see the skid marks of from the tires, right? You see, and you have to find if the vehicle was, what was the speed of the vehicle initially.
Could you show us how you would do something like that?
Well, you get to here and you say V naught is equal to square root of 2gx times coefficient of friction times cosine of theta minus sine of theta. Like this, right? From here, solve for V naught instead of solving for x. X is given.
You can do that for any of the variables. You can do that for the coefficient. For
Yeah. You can. Well, if the truck is not going downhill but going up, but uphill, and again the same story, the situation is going to be similar, but the final energy is going to. So if the initial velocity was this way,
you minus the weight plus.
so in that case, initial energy is going to have some only kinetic energy term, let's say. The final energy is not going to be zero, but it is going to be this gravitational potential energy, mgh. Right? It is, well, it is not going to be much different from that, yes.
Your initial would just be 1/2 of mass times V
Yeah.
naught squared,
Yeah.
It would not be plus the MGH, instead the final would be.
Because if you take the zero height to be here, the gravitational potential energy MGH is zero. But when it stops, it is at some height. But the procedure is pretty much the same. So I really don't know. I haven't written the test. I'll write it probably on Sunday afternoon. But the difficulty here is, so what people are going to do if I give a problem like this, they're going to just take this formula, memorize it, write it somewhere or whatever, and give me some number. And the grader is going to see that, and he's going to give 0 points for that. So avoid this. The problem is the process. The final number, nobody cares. Okay?
In the case, sorry, where it's uphill and work doesn't just equal negative energy.
Oh, it is going to be equal. The work is still going to be equal to negative.
The
good.
work would be equal to MGH, or the energy final minus the energy initial, right?
Yeah.
That'd be equal to what we found for our work of the frictional force.
Yes.
Okay.
So if you want, I can solve the problem also for the case, a different problem when the truck is going up rather than down.
Wait, so, quick question, it goes from a negative, why does it go positive? Cause your initial,
Yeah.
well, cause there's two negatives, I get it, never mind. Answer real quick.
Okay. Okay, so do you want me to do the same problem? Now truck going uphill, and again, sliding uphill until it reaches stop. Okay, it's a different problem. Well, okay. So maybe, okay, let's start from the very beginning. So you have again the same situation. Have again the same situation, but now, well, let me see. Okay, I can keep the same coordinate system, everything the same, except that the initial velocity now is in this direction, and this truck the brake slop at this moment, and the truck comes to a stop at this position, and they're asking us to find what is this distance, stopping distance again. Again, express the height of the final position using this expression from the right triangle that is on the board. And now you have initial energy now is only kinetic term, 1/2 mv0 squared, because the gravitational energy at the bottom is 0 because you're at 0 height. The final energy when you're at rest is going to be this height, mg, this height. In other words, it is going to be mg x sine. Okay. So you have initial, you have final energy. The friction force, again, here is the free body diagram. The slope, frontal, the angle, the truck at some point is somewhere here, and the forces acting on the truck are mg, normal force. Now the friction force now is going to be this way. Right. The friction force is stopping the truck. And again, you decompose the weight into a component that is perpendicular to the surface and parallel to the surface. Here are the two components of the weight. The component of the weight that is interesting for me, if I'm solving the problem using energy conservation, this is again the angle theta. And the component that is interesting is again the perpendicular component. And again, it is equal to mg times cosine of theta. And the rest is the same. The friction force is normal times coefficient of friction. And the normal force have to be equal in magnitude to the y component of the weight. In other words, it should be this. The work done by the friction force is going to be friction force again, multiplied by displacement, again multiplied by cosine of the angle theta. Now look, the displacement now is this way, right? The displacement now is this way. The friction force is again opposite direction, downward direction. So not theta, but cosine of 180. And again, cosine of 180 is again -1. The friction force is mg times cosine, so you have, this is negative mg, I'll write x first, and after that I'll write cosine of the angle theta. This is the work done by the friction force. And now the work energy theorem says the work done by the friction force should be equal to the change of energy. Change of energy, change of anything is final minus initial. So the work has to be equal to final energy minus initial energy. Okay, work is negative mgx cosine. Final energy is mgx sine of theta. And initial energy is 1/2 mv naught squared. Again, so now you have some minus signs that, well, you can keep or you. But cancel the mass first. Move the term that contains the unknown distance x to the other side of the equation with opposite algebraic sign. So it is going to this term is going to be negative gx sine of theta. You have negative gx cosine of theta. And this is, where is the coefficient of friction? I skipped the coefficient of friction. It's right here. The coefficient of friction is right here, right? Coefficient of kinetic friction is right here. So the work, this contains the coefficient of friction. So you have the coefficient of friction times gx. Is equal to negative v naught squared divided by 2. And now all terms contain a negative algebraic sign. I can multiply by -1, and all of those terms become with +1. So get this. Factor out again gx here, and you're going to get gx in the brackets you have sine of theta plus coefficient of friction times cosine of theta is equal to v naught squared divided by 2. And finally, solving for x, for the stopping distance x, you get v naught squared divided by 2 times g times sine of theta plus coefficient of friction times cosine of theta. You see that this result looks similar to the first one, but you have some signs, some algebraic sign is switched.
So did that 1/2 go to a 2 because you multiply it?
Yeah, yes, yes.
By two.
This 1/2, either you write it as 1/2 or you write it as division 2.
So either way, it's fine.
It is the same way. It is the same, just different way of writing the same thing. Okay. Okay, let's see. Questions, remarks? Okay, let's see other problems that you want. See, maybe common problems, maybe practice test problems, whatever you can come up with.
Energy final over there, the kinetic energy plus MGH.
The final energy is only MGH because of the top. The truck is at rest, right? It is, the brakes are locked. It comes to stop at some positions, and we're looking for the distance it covered. Well, it was in the process of stopping.
So if it was still moving, you would then put the kinetic energy.
So while it is, if it were still moving, it was going to have kinetic energy term. But luckily for us, it is not moving. Other questions, other problems? Okay, questions?
Sorry to ask so many questions. Going back to chapter 6 and 7, can you, I'm having a hard time just remembering what all of the, so like P, that stands for momentum, right?
Okay,
P
yes,
is momenta,
yes.
Ke is kinetic energy. What are the other, like, sometimes I forget which equations. I know you can give us all the equations, but sometimes I don't even remember what they stand for. I don't know if you can pull up maybe on the practice exam. You go up to the top to the equation sheet.
Let's see what equations we have here. So on the left, you have those kinematic formulas, right? They are not surprising.
Okay.
This
Net
is
force.
Newton's law of gravitation, universal gravitational constant, masses, distances between the two masses. This is how we calculate the 9.8 acceleration due to gravity as a product of universal gravitational constant, mass of the Earth, and radius of the Earth. What else? Here is how you switch between a period of rotation, the time for one rotation, and speed. So speed is distance divided by time. For one complete rotation, the distance is the circumference of the circle,
2 parts of circumference.
and t here is the time for one complete rotation. So
To reverse that, t would also equal speed times circumference.
it is
Or sorry.
so for t it is 2 pi r divided by v, right? But whatever is needed.
Can you say, so it's switching from one period of time to a full rotation? What is that?
Yeah. So a period t is defined as the time for one complete loop. Okay. And time is distance divided by speed. The distance for one complete rotation is circumference. So period is going to be distance 2 pi r, circumference, divided by the speed v. Right? This is correction that I probably even shouldn't even give that formula because it is kind of, but it is there. So what are the other formulas? This is the, well, it should, instead of subscript radial, I would say what we brought in the appropriate section. I think it was chapter 5, I think, was centripetal acceleration, a centripetal, but it is the same as a radial. It just tells you it is directed along the radial direction. Is v squared divided by r. The force corresponding to this centripetal acceleration is just mass times that acceleration. So the force is not given, but you should, right here, it is given. Here. So centripetal or radial direction shouldn't confuse you. They're the same. Directed to the center is radial direction. A formula for the maximum value of the static friction, a formula for the kinetic friction. Okay, so okay, this is something that we just did. Period, calculated if you know the speed. Now, this is the period of rotation in the case of a satellite orbiting the planet Earth. And basically, you have to derive this rather than take it for granted, because I don't even remember it. And the same thing here. This is the speed of a satellite that is orbiting at a radius r, a circular orbit with radius r. Again, I don't remember those formulas, and you shouldn't too. You should be able to immediately figure them out, because you have the Newton's law of gravitation. So we can derive them if you want, but don't try to memorize. Okay, now definition of linear momentum. Definition of impulse. So this is the impulse momentum theorem. The impulse is equal to the change of momentum. The impulse of a net force is equal to the change of linear momentum of the object. This is what we did yesterday in class. And after that, we haven't covered this material yet, but those are kinematic formulas that we're going to derive tomorrow. Well, not derive, I'm just going to write them because they're identical to the kinematic formulas for linear motion. You just have to substitute the linear displacement with the angular displacement, the velocity with angular velocity, acceleration with angular acceleration, and pretty much you get exactly the same formulas. So those are the formulas from the previous page, just do this substitution. What else? So they are not in the same order, it seems, but here's the definition for angular velocity. Here is the definition for angular acceleration, average angular acceleration. I don't know why, but the kinematic formulas are going to follow there. Yeah, here are the kinematic formulas. Now,
This joules and work be up there.
it should be somewhere in the definition. Yeah, well, I didn't. Yeah, you're right. I don't have the formulas for work and for energy. I've got those formulas.
Thank you.
Yeah, I shouldn't forget, but if I do, I shouldn't forget. If I forget to write those formulas, I'm going to write them on the board. But those are definition for kinetic energy, definition for gravitational potential energy, definition for work done by a force times displacement times cosine of the angle between them. Those are the formulas that I have to add if I shouldn't forget. Okay.
Okay, so there's, I'm probably remembering this wrong, but there's a big P and a little p, right? Or both, maybe, or at least in my notes. So does P stand for different things?
Oh, linear momentum P. I don't remember using it for anything else.
When we find like for power.
Oh yes, but it is for power. I usually use large uppercase capital P. So divided by time or energy change. So linear momentum is lowercase letter p. Power is, yeah, the definition for power also has to be added there. The work energy theorem that we used also has to be added. I don't know how I missed those formulas, but I did.
We did number 16 on the practice test.
Let's see.
I did one similar to it on my paper.
Yeah, this is the ballistic pendulum. This is another problem that we need to know. And this problem, they regularly give it on the final for the lab, but it may be slightly differently worded in the lab because you do this lab experiment with a projectile rather than with a bullet, right? So let's see. So you have this projectile, this bullet hitting the block. The collision is completely inelastic because they say that the bullet gets embedded in the block, completely inelastic, which means that kinetic energy is not conserved. You lose kinetic energy. The kinetic energy, part of the kinetic energy is converted into thermal energy, into the formation of the block and the bullet, into acoustic energy, all kinds of other energies, but part of the kinetic energy is gone. And well, this block together with the embedded bullet is deflected in such a way that it reaches this height. So the first question that they ask is to find the speed of the bullet plus block while it is still here, just immediately after the collision. And this is a question that you can easily answer because immediately after the collision, this system of bullet plus block has some amount of kinetic energy left in it. And that kinetic energy is converted into gravitational potential energy when the system gets deflected to this position. At this position, the system is at rest. So it doesn't have any kinetic energy at this position. It has only gravitational potential energy. In other words, whatever kinetic energy the system has immediately after the collision, that kinetic energy is converted into gravitational potential energy. So you have this. The system immediately after the collision has kinetic energy only. And that kinetic energy is 1/2 the total mass, because they are a single object now after the collision. Some unknown speed, which they say use the letter D final for that unknown speed squared. So this is the kinetic energy of the system immediately after the collision. Unknown, you cannot calculate it, but it is this expression. That kinetic energy is completely converted into gravitational potential energy, total mass times G times H. So this is kinetic energy immediately after the collision. This is gravitational potential energy when the system reaches its highest point. And from here you can solve, right? You can cancel the total mass, and you can say that the final is equal to square root of 2 times GH after. Right? You can answer that way part A of the problem. See questions?
That's for A.
That's for A, yes. Part B, find the speed of the bullet. So the speed of the bullet, energy is not conserved. Kinetic energy is not conserved. Mechanical energy is not conserved. During the collision, you lose energy. But what has to be conserved is momentum, linear momentum. So you want linear momentum initial to be the same as linear momentum final. I'm not going to, well, vector signs are not needed because before the collision and immediately after the collision, all the vectors are along this horizontal direction. So vector signs are not needed. Well, the linear momentum before the collision is only due to the moving bullet. The wooden block is at rest, so it doesn't contribute to the linear momentum. So the linear momentum before the collision is the mass of the bullet. What is it? M1 or M1, yes, multiplied by the unknown speed of the bullet V01, V01. This is the initial linear momentum. After the collision, at the instant after the collision, now you have a composite object with mass equal to the sum of the masses, times, to get the final linear momentum, you have to multiply by the speed of this composite object immediately after the collision, and you already have calculated it. This is this speed. Right? This is, and you have an expression for that speed. You have this algebraic expression for that speed. And from here you can say the speed of the bullet is equal to m1 plus m2 divided by m1 multiplied by v final, and v final you can say is 2gh. So this is part B. The speed of the bullet just before the collision should be this expression. And part C is how much, what percentage of the initial kinetic energy is lost. So look, you have kinetic energy before the collision is 1/2 the mass of the bullet times the speed of the bullet that we just calculated. This is the initial kinetic energy just before the collision. After the collision, the kinetic energy after the collision is immediately after the collision. Look, that kinetic energy, where is it? It is this one. And immediately after the collision. But so it is 1/2 m1 plus m2 times the final squared. But that kinetic energy is also this gravitational potential energy. So if I want, instead of that kinetic energy, I can use the shorter expression, this mgh. It's equal. So energy lost, kinetic energy lost is equal to the difference between the initial and the final. So it is kinetic energy initial minus kinetic energy final. In other words, it is 1/2 m1 v initial squared minus, well, I'll use this expression for final kinetic energy just because it is shorter. minus M1 plus M2 in brackets times GH. This is the kinetic energy lost. And they're asking us to find the percentage that is lost. So they're asking us to find kinetic energy lost divided by initial kinetic energy multiplied by 100%. So in other words, it is going to be the loss is 1/2 M1 V initial 1 squared minus M1 plus M2 times GH. And the initial is only this divided by 1/2 M1 V initial 1 squared. So you can now substitute this and this with what we calculated for the initial energy. Where is it? With this expression, you're going to get unpleasant arithmetic. Are there alternatives? Yeah, you can divide. So this is multiplied by 100%. The alternative is divide this to this, and that division is going to give you 1 minus this to this. M1 plus M2 times G times H divided by 1/2 M1 V, not 1, that's like this. So again, all of this has to be multiplied by 100 to get your percentage. And now you don't have other options, but you have to substitute V initial 1 of the bullet with this expression. It has to be squared. You're going to get some cancellations. So probably you're going to get, where should I do it? Let's do it here. So when you substitute here, you're going to get, so the number that you're looking for is going to be like this, 1 minus M1 plus M2 times GH divided by, well, 1/2 M1. So V initial squared, so this V initial squared is going to give you M1 plus M2 divided by M1. This is squared, this is squared, and the square root is going to disappear, and you're going to have 2GH. And you see, you're going to have multiple cancellations. So you're going to have 1 minus, let's see what you're going to cancel. So you can cancel GH with GH here. You can cancel this 2 with this 1/2. You can cancel this power of M1 with this. You can cancel this power with this. And after all those cancellations, the result is going to look like M1 divided by M1 plus M2. So you can do the division, divide this to this fraction. You can do it in different ways, but the result is going to be like this, and you have to multiply this result by 100%.
How did you get an M1 on the top?
Well, M1 was here, M1 was here, and the rule for division of fractions, right? So P divided by Q divided by L divided by M. The rule for division of fraction tells me do P times M divided by Q times L. Right. This is, so for me, M was M1, it came up there. Again, fractions, dividing fractions, you can interpret it in multiple ways, but I practically do it on the fly. You have to spend some mental energy.
I still good for after Friday, after class on Friday.
Yes, of course. What time was the class for you?
11.
From 11. So you want from noon?
Yeah.
Okay.
Thank you.
Keep in mind that your version probably is going to be different,
For sure.
because I'm not going to write the test before the weekend. Yes.
So you multiplied by 1. And I'm confused at that process there.
Yeah. So here, from here to here, right?
Correct.
So you have, I'm using this A plus B or A minus B divided by A is equal to A divided by A is 1 minus B divided by A. So A, B, A, this.
Okay.
This-
Because the 1/2 mass 1 V naught 1 is on the top.
So
and the bottom
this divided by this
is 1.
minus this, yes, minus this divided by the same thing.
So it allows you to cancel out the one on the top.
Yeah, well,
Cancel.
yes, but again, you can do the arithmetic in many different ways, and this is just one way that I did it. But you can do the arithmetic in many different ways. Okay,
Hard to keep track of everything.
yeah, well, if you just have to spend time. So when I was undergraduate student, after class, I was spending at least several hours to rewrite my lecture notes. And this you do it if you have the time. It is always a matter of, do you have the time or not? If people had the time to study physics, everybody was going to have a PhD in physics, if that person wanted one. So okay, let's see other questions, other problems. So tomorrow in class, I have to practically spend the entire class time for chapter 8 to make sure that we're done with that chapter. And on Friday, if you have questions about homework problems, about practice test problems, this is going to be the only time that we're going to have on Friday during class to answer if you have additional questions. Okay, last time, any other problems you want to see today?
Can we expect something like this on the test?
I don't know. I probably would give something of this type, but I'm just afraid that people are not going to do well. So the last problem on the homework assignment on chapter 7 was practically calculate something like this. So you should expect maybe something like this. And I can modify the problem, find the percentage of energy that was lost, find the percentage of energy that remained in the system. So you can do variations of this type. Yeah, you should be able to do something of that type, like part C of this problem.
And to find the energy that was remained, you can just find the energy lost and subtract it from 100.
Well, it just is easier to say Energy lost is what? It is energy lost is kinetic energy initial minus kinetic energy final. So this is your energy lost, kinetic energy lost. If I want to see how much energy, what percentage of the energy is left, I just say kinetic energy left divided by initial. Much simpler. Right. But you can always do arithmetic like this. It's just simpler to think this way. So this is problem, I think the last problem from the homework assignment for chapter 7. I think. Yeah, prepare this, you to realize, keep in mind that kinetic energy is lost in the case of inelastic collisions. But linear momentum is always conserved. Elastic or inelastic collisions, linear momentum is conserved. Okay, let's see other problems and questions. Not, let's continue with chapter 8 tomorrow in class. Okay, I'm going to email this recording.